understanding of first and second derivatives, those have a direct application into particle motion. So today we're going to look at what we call rectilinear motion or kinematics. That's the idea of a particle moving only vertically or only horizontally. So today let's look at this first one. This particle is moving along a horizontal line, and we're going to be dealing with time here. So its position at any time is given by this equation. We generally use S to indicate position. Then we'll use V for velocity and A for acceleration. Again, taking note in the prompt that the unit is in meters and seconds, because obviously that is going to come into play. So to find the velocity, again, we're applying our knowledge of first and second derivatives directly to particle motion. So velocity is going to be the derivative of position. So I like to make that connection in the notation. So S prime of t is V of t. And I know how to take this derivative because it's just a power rule. So I'm going to have 6t squared minus 14t plus 4. Right? So find the velocity at time t. That's what I just did. So that was kind of the question, or the answer to question 1, right? So that's the velocity at any time. And now I also want to know the velocity when t is 1. So the notation for that requires that I plug a 1 in for time. And then I'm going to show computations, right? So I'm going to show what I actually did. Then I'm going to end up with 6 minus 14 plus 4, which is negative 4. But the unit really matters here. So this is a rate of change. So because I was dealing with a derivative, this is going to be in meters per second. So that is my velocity at t equals 1. So we're going to take some of that information, we're going to apply it to 1b. When is the particle at rest? When is it moving left? And when is it moving right? This is a direct application of the first derivative test. I can tell when a function is moving positively or negatively based on its derivative. So if I want to know when the particle is at rest, that's going to be when the velocity is equal to 0. That's also going to be where I could possibly be changing direction. So that's going to be my first step in this process, right? So I've got S prime of t is going to be equal to 6t squared minus 14t plus 4. I had already done that, and I could have labeled that as v of t. That would have been fine. But now I need to factor that. I need to set that equal to 0. So I'm going to show that step that I am setting the velocity equal to 0. And now I'm going to go through the factoring process. The GCF, if I do not get the GCF out, this is going to be a very tricky situation. So then this does factor, right? So I'm going to end up with a situation where I'm going to have a 2 and a 1 here. So it's just the order in order to get to a negative 7. That's what I'm looking for. And the sign does have to be the same. So this is going to end up being a negative 1. And this is going to end up being a negative 2. And I want to know where that's equal to 0, of course. So I'm going to take each piece separately, each factor. I'm going to set it equal to 0. I jumped ahead, didn't I? So this is going to be t is equal to 2, and this is going to be t is equal to 1/3. So remember, those are my critical values. This is an application of the first derivative test. So those are where I could be changing direction. I could be going from increasing, which is the same idea as moving right, to decreasing, which is the same idea as moving left with particle motion. So I'm going to do my sign chart. But now when I label it, I'm not labeling it as f prime and f. I'm labeling it as v, right, or s prime. So either one of those is fine. And s. And then my critical numbers are going to be 1/3 and 2. This prompt was specific in that t is only going to be greater than 0. That's pretty common with particle motion questions, but we want to pay attention to that. So now, let's take values on the left side of 1/3. Right? It's basically just 0. That's really all I have to look at. But obviously I could have other values there, but that's the easiest one to look at. If I take that and I plug it into this derivative, I'm going to have a negative times a negative, which is going to yield a positive value. Which now, because I'm working on a horizontal line, that indicates a right movement. It does not indicate increasing or decreasing, but it does indicate right and left. So now, between 1/3 and 2, the easiest value is probably 1. So this is going to give me a positive. This is going to give me a negative. That indicates a left movement. And then if I plug in a number bigger than 2, you'll have a positive and a positive. So again, we're going back to the right movement. So to answer all of the questions, I had to use the first derivative test. I needed to use that sign chart to get everything organized. And now I just need to go through my explanations. So when is the particle at rest? So particle, I'm going to do some abbreviating here. Particle at rest at t equals 1/3 and t equals 2. But the reasoning is because the velocity is 0. Because v of t is equal to 0. You could put s prime, right? That's okay. But we like to make the connection between those two. So that's my justification for this. Now let's talk about where am I moving right and where am I moving left. So the particle moves right. And then I need my intervals. Now I am going to go from 0 to 1/3. I'm not going to go from negative infinity to 1/3. And then from 2 to infinity. Your justification is because your velocity is positive. That's what your analysis, your calculus analysis allowed you to determine. And then particle moving left is just the one interval. You're going from 1/3 to 2. And again, your justification is because your velocity is, you could just put less than 0 if you wanted to put that, right? Or you could put is negative. But that is your justification. We got to practice with our justifications at this point in this class.